Hello, everyone. We are picking this up now. We're on page 44, bottom of 44. We're talking about phosphines. And phosphines, I know they were in the organometallic section, so we're talking about metal carbon bonds, but phosphines are still an extremely important ligand type in organometallics because they show up quite a lot. They're really good to stabilize lots of these organometallic complexes, and we'll see why in a little bit based on their electronics and sterics. Pretty much they're neutral ligands, so they can exert a strong influence on steric and electronic properties, just like what I discussed. So we know what phosphines look like, where you can have 3 bonds to phosphorus, generally carbon-based, but of course we have different ones, and you have your lone pair of electrons. So this is what's generally forming donation to the metal center. Now, common ones that you guys would know about, we have our trialkyl phosphines. So that would be stuff like trimethylphosphine, triethylphosphine, and of course triaryl phosphines. These are ones that you guys have also seen so far. So that would be triphenylphosphine that we've discussed in class. And of course, you know how you can have bidentate ones as well. Okay, that would be the dimethylphosphinoethane, the bis-dimethylphosphinoethane. We saw similar ones to those in our list of ligands back when we did coordination complexes. So the main way that these guys bond, like I said, is through sigma donation. So donating electrons to the metal, so sigma donors, but they can also be pi acceptors. So if you think about what else, sorry, we're on to the next page now, by the way. If you think about what else phosphorus has around it, there are a few ways it can accept electron density. One is into the empty d orbitals that it has. So we have our metal d orbitals, and then with phosphorus, those are empty. So we can have back donation from the metal to the phosphorus. But another thing that it has is pi or sigma star orbitals on PC. So when you have phosphorus carbon bond or whatever phosphorus is bound to, it has 3 of those. You do have pi star or sigma star orbitals on either side. Those are your sigma star orbitals. Those guys are empty, and so you can have donation into those guys as well. And you'd have to do a lot of calculations to figure out exactly which one of these involved, but both of them can be involved. Now, steric effects of phosphines. These can be extremely wide-ranging depending on what you need. If you need to pause the video, go ahead and write down all this stuff, by the way. But I'm going to keep going. You guys write at your own speed. Okay. There's something called the Tollman cone angles. So let's say Tollman came up with this stuff. And it's just a way of gauging the size or the amount of space that each of these phosphine ligands will take up. So if you picture a metal phosphorus or phosphine compound, and you have these 3 ligands coming off. This is trigonal pyramidal on this end over here. So you can picture kind of like a cone over here. And the amount of space that it's taking up is kind of defined by this cone. So this is the Tollman cone angle. Okay. And if you want to compare some, let's say, so PF3, so trifluorophosphine, that's about 104. And then we just get bigger. So switching a phosphine with a methyl, we're up to 118. Switch a methyl with an ethyl, 132. Have a phenyl, 145. And a cyclohexyl, which takes up even more space, 169. So depending on the type of space that you need for a particular reaction, or you want to protect certain sites on your metal, you can just vary the size of your phosphine donor that's on there. Now that was the steric effects, but we can also look at electronic properties. I'm down a bullet point here. And if I kind of write out a list of them, I'm going to do, yeah, we'll erase this now. Make sure you have that all written down. I'm going to write out quite a few here, starting with PCY. The CY is cyclohexyl. You can get that from the last one. Triethyl, trimethyl, this is the triphenyl, this is trimethoxy, so kind of like an ether bond almost. I'm going to make that over here now. This is the phenoxide one. Oh, sorry, 3 of those. And then getting into the halogens. Okay, so this list here, if you can imagine on your pages, stretched right across. The difference is really in these two sides, we have more electron donating substituents and electron withdrawing substituents. So this end is electron donating substituents. Over here we have electron withdrawing substituents. So if you think about it, if these are electron donating substituents, they're giving more electron density to that phosphorus. So that phosphorus, you have more electron density that is now able to be given to M through a sigma bond. So this increases the Lewis basicity. They're more Lewis basic, and it also makes them better sigma donors. Okay, this makes a really strong bond with particular metals. So if they're good sigma donors, that means they're giving more electron density to the metal center. And so what you want to have in those cases is a metal center that is relatively electron poor. Okay? So they're good. Let's write that down here. Make strong bonds with electron poor metals. Okay. Okay. Now let's move on here. The next part. There's an example here. I'm just trying to pull it up. I didn't actually have this printed out in English. Oh, actually, no, let's finish over here. Right. So with our electron withdrawing substituents, you can kind of picture the opposite is happening now. So they're pulling electron density away from that phosphorus, which means you're going to have a weaker bond. So we're now, these are electron poor ligands. So you can picture they're going to be better at pi accepting, right? So they're going to be better pi acceptors. So increased back bonding from the metal, right? I'll put that on here, increased back bonding. So these are going to be good with metals that are electron rich. Those ones that need to divest themselves of some electron density, just too much electron density. Okay, so let me pull up my example here that we had. So the example, which complex has the greatest CO stretching frequency? This is pulling in some of that material that we did learn while school was still going on with CO, and now kind of comparing with some phosphines. Okay, so just as a bit of an aside, if we remember metal carbonyls, okay? So they're good sigma donors, but they're also good pi acceptors into, and I'll just really quickly here, those pi star orbitals, okay? That's the pi star, so an empty pi star, you have that going on. So if you think back to what we learned in class, the more electron density on the metal, the more it's going to give electrons back to CO. If they're back in CO, This is an antibonding orbital. What's going to happen is it's going to weaken this bond right here, okay? If it stretches that bond out, then we're going to increased back bonding, I'll just say BB. You're going to have increased bond length, that CO bond length. And what's going to happen to that stretching frequency in the IR is that it's going to go down, okay? So that's just an aside, just from before. And now we're going to see what happens when we're changing a different phosphine on metals, what's going to happen to the CO. So our example, really everything is the same except for the phosphine donor. So you're looking at the triethylphosphine versus the triphenylphosphine, okay? So think about each of these cases. This one here is more electron donating than this one, right? So you're going to have increased sigma donation. So you're going to have increased electron density on the metal. And if that's the case, you're going to increase that amount of back bonding that you can do to CO. So increased back bonding to CO. So going into that pi star orbital. And when that happens, that stretching frequency of the CO is going to go down, okay? So that's kind of your answer there. This one will be a lower stretching frequency, and this one will be a higher stretching frequency, okay? Good. Now, next part, let's move on to hydrides. So that was phosphines. So in this video, I'm just going to cover phosphines and hydrides, keep it short and bite-sized for you guys. Hydrides and hydrogen. So every time we looked at hydrogen, if you're looking at it in most other complexes, let's say in carbons or bound to halogens or bound to oxygen, the charge is generally going to be +1, right? Is what we normally look at. But it really depends on what it's bound to. So if it's bound to something that is less electronegative than it, so if it is the one that is more electronegative, it's going to take the electrons. It becomes a negative ligand. So when it's with metals, it's H-, and that is called a hydride. Okay. So the way that you create these bonds, your hydride, which has a lone pair of electrons on it, and donating to the metal. These are all found in the 1s orbital of hydrogen. That's what it is. Some details on this, if you're to do an NMR, where does this hydrogen show up in NMR? Not our typical organic range between, say, 0 and 12. We're looking at values -50 to 0, which is pretty crazy. In the IR, it's pretty characteristic. You're looking at that MH stretching about 2850 to 2250. So not much shows up in that range except for, say, CO2 in the atmosphere and a few other things, but not that much else in there. And looking on XRD. So our XRD is looking at X-ray diffraction. It's diffracting from areas of electron density. Now, hydrogen really doesn't have much electron density, so you don't really see much in XRD. Now, next point. Hydride can also act as a bridging ligand. So when it's hydride, really simple. This is the story, okay? But can get a little bit more interesting. So when we're talking about it being a bridging ligand, you can see compounds like this being generated. Okay. Now this is a little odd because if you think about it, hydrogen only has 2 electrons to give, right? And generally when we're talking about bridging complexes like this, like let's say you guys have seen complexes like this, right? So these are made up of a lone pair like that, another lone pair like that, right, on the chlorine. So each bond is made up of 2 electrons. Well, in this case, hydrogen only has 2 overall, and it has to make 2 bonds and cover 3 centers. So what we call these ones here are 3 center, 2 electron bonds. Okay? They do exist, so it's really a delocalized orbital, if you will, that is containing the 3 different atoms and 2 electrons found within that delocalization right there. Okay. Now, hydrogen also uses electrons from its sigma bond. So if we want to have bonding to hydrogen, by hydrogen I mean H2 gas. Let's see how that can happen. So H2 gas, really simple. It only has 2 electrons. They're found in the sigma bond, but they can donate to find or to form a bond with a metal. Okay? So you can get, this is called side-on bonding. Okay, and it's a neutral ligand. You're looking at electron counting. It's worth 2 electrons because those 2 electrons are being donated to the metal or forming a bond with the metal. Okay, so really it's like having those 2 electrons there in that sigma bond being given. So this is sigma donation to M. Now you could also have back bonding. So like pi backed on, it's a pi acceptor. So if we look at our metal, we know we have all these lovely d orbitals. Okay? Then if we draw out our H here, there's our bond that was created, like that. We also have this antibonding orbital here. This is the sigma star antibonding orbital, and it's empty. So you can have back bonding from the metal d orbitals into the sigma star of H2. So this is showing that H2 is a good pi acceptor. So you're getting back bonding. And that'll depend on how much electron density the metal has. Now, in terms of how much back bonding you can actually have going on, I'm just going to kind of show you the 2 different extremes here. So let's say we go from the case, I'm just going to draw them this way now, where you just have pure sigma donation. Okay, let's say this metal is N+ oxidation state. Now, as you increase your back bonding now, you're starting to create bonds here. And as you're adding to that sigma star, where that's an antibonding orbital, you're weakening the bond. Okay? So what you end up with, put the H's in here, you end up weakening that guy, creating some new bonds, something like that. And then if you increase our back bonding again, eventually you're going to get to the state where you've actually broken that bond and created 2 new bonds. Okay. Yeah. In this case here, now you've gone from Mn+ to Mn +2. This is called oxidative addition. And we're going to talk more about these different types of reactions that we see in organometallic chemistry. But that H2 was reduced. Your metal was oxidized, H2 was reduced. Okay, so I'm going to stop there for hydrogen and hydrides, and I'll pick up the next ones on the next video set.